So you need to persist data across runs of your game, huh? You've come to the right place. In this video, we're going to take a look at how you can do that without using player prefs, because that is not the right way to do it. We'll start writing files to the disk and reading them, specifically using the JSON format in this video. Later on, because JSON's very easy to read, we'll also take a look at how you can make it a little bit harder for your players to modify that data directly. Hey, Chris here from LlamAcademy, here to help you.
Ooh, me?
Yes, you. Make your game dev dreams become a reality. Persisting data across runs of your game is something that many games need because you want your player to be able to resume wherever they were if you have any kind of progression in your game. RPGs, maybe you need to store stuff like inventory states, quests that have been completed, their stats, all this kind of stuff. And you want them to be able to not have to get that at the beginning of each round of their game. I've seen a bunch of tutorials telling you, hey, here's how you persist your game state using the player prefs, and that's not the right solution. And a lot of the other ones that don't tell you to use player prefs tell you to use dangerous classes like the binary formatter. Player prefs is designed to allow you to store data about the preferences of your player, so that way you can have things like customized audio settings, customized graphics settings, data that you can afford to lose without it really making an impact on your game. The API for storing data with the player prefs also isn't very conducive to you using it for storing game state. You can only set strings, floats, and ints. Having things like dictionaries, lists, this kind of stuff isn't really easy to do. Also, the player prefs, at least on Windows, is stored in the registry, which isn't designed for large quantities of data and really isn't a great place for you to store that in the first place. So if we shouldn't use player prefs because it's not designed for that kind of data and it's stored in kind of questionable places, how do we store data for persistent data? Enter in application.persistentDataPath. This is a property on the application class that will tell us exactly where we can write files to, and this path will not change as long as you're not changing the player company or name of your project. Changing those two things will affect where you're going to store this data. So even across different versions of Unity, as long as you don't change those two things, you're safe. So we know where we can store data, but how we store data is also an important consideration. We're using text-based serialization, storing it in a JSON format, which is really a human-readable format. This is convenient because there's a lot of tooling in place in C# and many other languages to use JSON and XML types of serialization. The downside to this is it's relatively slow compared to some other ways, and because it's a human-readable format for both JSON and XML, your players will have a very easy time knowing what to modify if they want to kind of cheat in your game. Later on in the video, we'll talk about how you can make it harder, not impossible, but harder for where most people won't be able to do it just out of the box. One key thing anytime you're talking about persisting data is if you're storing it on the player's local machine, you just need to assume they have full control over that data and they have the ability to cheat, modify that data because they have full control of the machine that data is stored on. If you want to make absolutely sure the player cannot modify their source data here, you have to store that not on the player's machine. For most of us, most of the time, it's probably fine to store it on their local machine. It's also significantly cheaper because you have to pay for that storage. All right, with all the disclaimers out of the way, let's talk about how do we actually do this JSON serialization. First off, I would not recommend using the JSON utility class that Unity gives us. It's relatively slow and it can't serialize everything into a JSON format, which makes it kind of pointless for complex data types. Instead, we can use the JSON.NET library, which is one of the most popular JSON serialization libraries in all of C#. Unity also provides us a package that will allow us to bring that into our Unity project very easily. I couldn't find it on the Unity registry, which I found was a little bit weird. So instead, what you can do is go into your manifest.json file, which you can find here, edit that and add in this line of text, and that will add that as a dependency that Unity will then automatically import for you. I'm hopeful because I'm using Unity 2021 LTS that maybe in Unity 2022, this will show up on the Unity registry. Not really sure why it's not there. This is how you do it, even though it's not on the registry in the package manager. The cool thing about using JSON.NET here is we don't really have to do anything additional to make our classes able to be serialized into a file. We can simply do JSON convert.serializeObject and deserializeObject to convert from a string to an object and from an object to a string. This makes it where it's really easy. You don't have to think about it very much whenever you're thinking about how am I going to construct my data. You keep it in the same data model that you're actually using for your game, and that's kind of it. Let's hop into the Unity editor, check out the sample scene, and implement serializing some data with the JSON serializer. In the Unity editor, you can see the sample scene that I have two buttons at the top, one to serialize JSON and one that will just remove a file. That's a clear all data button. In the middle, I have something about enable encryption. We're going to get into that a little bit later. Let's start off just simply, how do we serialize some objects into a JSON format and save them on the disk? If we click play, you'll see the data in the format that we want to serialize. We've got some player object that has health, a name, a base attack speed, a level, some unlock stuff, equipment, and an inventory. So we're going to save all of this data onto the disk in exactly this format, actually. Remember, the whole project is available on GitHub. You can go in there, check out the repo, download everything here to see it in depth of how I set it up. The models and stuff like this aren't really important for what we're talking about today, just that we have complex data types that are being stored into a JSON format. So I'm going to create 2 new C# scripts. One that's going to be an interface defining how we will store data, and one of them will be the JSON implementation. If you follow this format, then you can implement new data storage formats that maybe a little bit later we'll talk about some of those. The first one we'll call IDataService. We prefix it with an I, indicating it's an interface. That's just kind of like a C# standard thing. And I'll make a second one called JsonDataService, keeping the data service part so I know it's a concrete implementation of the IDataService class. In the data service, because it's not a mono behavior, it's just going to be a simple C# interface, what I'm going to do is remove the extend mono behavior, change it to an interface, delete all the middle stuff, and define the interface that I want to implement. So what functions should any data service implement? 1, it's going to return a bool, whether it's successfully saved or not. It's going to be called save data. We're going to put angle bracket T angle bracket, which is how we define that this is a generic type here. So that way we can save any arbitrary data type. It's going to accept a string of relative path, a T data. So that's the data that we want to save that's of that T type, and a bool encrypted. And we're going to come back to that later. For now, we're just going to ignore that that's there. I just don't want to have to come back and modify the interface later. The second function will be load data. We're going to follow the same generic thing here with T load data, angle bracket T close angle bracket, saying that we're going to return the generic type here. It'll also accept that relative path and a bool, whether it's encrypted data or not. For getting us started, I think that's all we need to do. Now we've defined the interface type. Let's go ahead and go over to the JSON data service and implement the concrete implementation of this interface. On this one, instead of mono behavior, because we want this to be a simple C# class, we're going to extend only the IDataService. You'll notice it's complaining, so we'll go ahead and implement that interface. I'm going to rearrange them because we're going to start with saving first. Instead of throwing an exception, let's actually do something useful. So we'll start off getting the path that we want to write to. Remember that that's at application.persistentDataPath. So we'll do string path equals application.persistentDataPath plus the relative path. Then we need to check a couple of cases. One is if the file already exists, then we're going to want to delete that and just write a new file. If it does not yet exist, then we're just going to write the data to that file. So if the file does exist, let's first do a try block to say if something fails here, we're going to want to catch that exception. We'll just do a debug log informing us that, hey, this file exists. We're going to delete the old one and write a new one, just so that way we can kind of trace through the console what's happening here. We'll delete the old file with file.delete at that path. And we'll do using file stream equals file.create at that path. And we're going to want to immediately close that stream. If we don't close it immediately, then we will not be able to write to it. We'll get an exception saying this file is already in use. Because on the next line, what we're going to do is file.writeAllText, passing in a path, and then JSON convert, which comes from the newtonsoft.json namespace, .serialize object, passing in the data, and then we'll return true. We'll also catch the exception E. If anything bad happens in that whole process, we're going to just debug log an error, telling us what that error was, and then return false. That's really all we have to do to serialize a JSON piece of text. This file.writeAllText at the path, and then JSON convert serialize object. So JSON convert serialize object does all the heavy lifting of converting whatever data we have into that JSON format with a single line of code. That's pretty cool. In the case where a file does not exist, that'd be the else case of our if block here, we're still going to need to do the try catch. So we'll do try. In this case, it's a little bit more simple. We don't have to delete a file first. So we'll just tell us that we're creating the file for the first time, and then doing using file stream equals file.createPath, passing in the path again. Again, we're going to close that immediately and then write all the text to the file. This is almost the exact same thing we did before, just not deleting the file first, which means we can actually condense this, where the only thing different is we will first check if the file exists, delete it, otherwise we'll just log that we're creating the file for the first time, and then do the exact same piece of code. Cool. Let's see how that looks in the demo. In the demo class, the first thing we'll do is create an IDataService and initialize it to be a new JSON data service. We'll create a new public void, serialized JSON, and we'll check in there if DataService.saveData, passing in some path, we'll just do /playerstats.json, passing the second argument being that playerstats data object, and we'll pass in encryption enabled, even though we know that does nothing so far. Because that returns true or false, we can check else. That means it failed to save, and then we can log an error and set maybe the input field text to be some error message. But we set this up where nothing happens if this returns true. So why don't we just log how long it takes so that way we can check out the performance of serializing this in a text-based format. To do that, we'll make a private long called saveTime. In serialized JSON, what we'll do is define a long start time equals datetime.now.ticks. After we've completed that saved data means some time has elapsed. So we'll do saveTime equals datetime.now.ticks minus the start time. So that'll give us a difference in ticks, which if we divide the ticks by 1,000, I'm sorry everyone, this is supposed to be 10,000, not 1,000. You can also use timespan.ticks per millisecond instead of a hard-coded value here, and that will be better and more accurate. So on all of my times here, you can move the decimal one place over. That will give us the number of milliseconds that it took to perform that operation. So let's go back to the Unity editor and see how does this work in action. Under the Canvas button container serialized JSON button, I'll add a new on-click listener, drag the demo script from the canvas, and set it to be demo.serializedJSON to be the action that we want to take. Let's go ahead and click play. If I click serialized JSON, we'll see that it took about 40 milliseconds. Now, at the persistent data path, which is on Windows, this path, where this part is your username, this part is the company name, and this part is the project name. We'll see playerstats.json shows up here. If we open that up in Visual Studio, we'll see exactly what we saw there, just not formatted properly. If I quickly format this, you'll see the exact same thing that we saw in the Unity editor, just in a file. That's exactly what we wanted to see here. Now we have a way to save that data. How do we get it back after we've saved it into our game? We'll open back up the JSON data service and implement that load data function. In here, we'll define string path equals application persistent data path plus relative path, just like before. We'll first check if the file does not exist at this path, then we're going to log an error saying we can't load the file at that path. I noticed I typoed it here, I'll come back and fix that in a second, and that the file doesn't exist. Then we're going to throw a new file not found exception telling us that the path does not exist. This is important because whenever we're loading the data, we want to receive that data back. So if we can't get that data back, we're going to throw an exception. That way any consumers of load data can put a try catch block around and appropriately handle those scenarios. That somebody is probably us. Next, we'll do try tData equals JSON_convert.deserialize object of type T, which is the inverse of serialized object we were doing before. And in there, we're going to input a string, which is just going to be file.readAllText at this path. And then we're going to return that data, assuming that returned successfully. So if for any reason we can't read the text of that file, or that does not conform to the object structure that T expects, then we'll get an error, an exception will be thrown, and we're going to catch that. Whenever we get that, we're going to log that error saying we couldn't load the data because of whatever that error is. And then we're going to rethrow that exception. So that way, again, whenever we're going to call this, we can handle that in our calling code to maybe show something on the UI or whatever it is we're going to do. So if we hop back to the demo script, let's just make it where we'll load the data immediately after we've saved it and show it on that text input field on the right side. In the serialized JSON method, what we'll do is immediately after we've saved that, we're going to set the start time to equal datetime.now.ticks, and we'll try to read that data. So we'll do try player stats data equals DataService.load data of the player stats type. Pass in the same path we did before, playerstats.json. Again, whether encryption enabled or not. Then we'll set the load time to be datetime.now.ticks minus start time, exactly as we did before. And if we've gotten this far, that means we successfully loaded the data. We have not thrown an exception yet. So we'll set the input field text to be loaded from file, then a new line, and then we're going to just reserialize the same object with JSON_convert.serializedObject data, and set the load time text to be the load time in a millisecond format. We'll catch if any exception was thrown, log an error, and show that text on the input field that we had an error. We'll quickly hop back to the Unity editor and try it again from the top. So we'll serialize the JSON, and we'll see I forgot to format it here, so let's go back real quick. Whenever we serialize the object, we can optionally indent it, so let's do that on the JSON convert serialized object. We serialize it one more time. It took us about 360 milliseconds to load it and serialize it back into objects. But overall, now we can easily save and load data to the file system that will persist across runs of our game. The challenge that we have, of course, is that it's very easy to modify this data, and it's a little bit slow, which I mentioned earlier. Text-based serialization is not particularly fast. It is just particularly convenient to use. So let's take a look at what we can do for this enable encryption option. Thank you to all of my Patreon supporters. I am so grateful for your support. Every one of you is helping this channel grow, reach more people, and add value to more people, and that means more people are making their game development dreams become a reality. If you want to join this cause, you can go to patreon.com/LlamAcademy, get your name up here on the screen, and get a voice shout out starting at the awesome tier. Speaking of those awesome tier supporters, I have Andrew Bowen, Gerald Anderson, Autumn K, Paul Berry, Matt Arkin, and Ivan. I'm so grateful for your support. Thank you. I want to be really clear that this is not foolproof because there are some secrets required for encryption, and these secrets, if we're not storing them remotely somewhere, have to be included in your build, which means somebody can decode your build and find them. In this case, I'm using this key and this IV initialization vector, which got automatically generated for me earlier. I'll show you how you can get new ones because you should not reuse these because these are publicly posted on the internet. These are really bad for you to use now. It's important that these stay secret and are not easily exposed, at least, because once you have this key and this IV, you can decode it just like the application can. And that's why it's not particularly secure to do it this way. But what this does do is blocks anybody from just opening up the file in like Notepad and modifying the values. To save encrypted data, what we need to do is basically write data to the file that is already encrypted. So to do that, we're just going to make a little bit of modification to our save data function here, where after we create the file stream, we're going to check if it's encrypted. Then we're going to call a function called write encrypted data, passing in the data and the stream. Notice here we're not closing that stream because we need it to be open still. I'll add an else block that closes the stream and writes all the files of the text exactly as we did before. And then we'll still return true after either one of these works, because if there's an exception thrown at any point, we're going to hit that catch block and return false. So we'll define that write encrypted data function here with private void write encrypted data that accepts a type parameter. We're going to have that T data in a file stream that come in as arguments. And this is the general process that you're going to use whenever you want to encrypt data in C#. We're going to use the AES algorithm. And to do that, we're going to do using AES provider equals AES.create. That creates us a new instance of the AES provider. There are some other subclasses of this AES class, but you should not be using those. Almost all of them are deprecated, maybe all of them. Microsoft recommends you use this way to create new AES instances. From here, it automatically generates us a key and an IV, but because we're going to call this and get a new one each time, that's not going to work for us because we want to be able to decrypt the file later. And the next time that we try to load the file, if it gives us a random key and random IV, we're not going to be able to decrypt our file. We need to have a known key and a known IV to encrypt and decrypt our files, and they need to be the same each time. So for this, we're going to override the key and the IV that they give us with convert.fromBase64 string, the key and the IV respectively. Now we've set up, hey, this is how we're going to encrypt our file. From there, kind of some boilerplate that you basically always need to do is get a crypto transform and a crypto stream. So that's using iCryptoTransform. Crypto transform equals AES provider.create encryptor because we're encrypting data. And then using crypto stream equals new crypto stream, passing in the stream that we want to write to, the crypto transform that we just created that's going to transform our data for us, and the crypto stream mode of write because we're going to write data to this stream. So it's going to write data to that file stream that we passed in as the first argument, running it through that crypto transform that has the AES key and IV that's going to do that encryption for us. So we'll do cryptostream.write that accepts some bytes, not some strings. So what we're going to do is encoding.ascii.get bytes and then pass to it the serialized JSON object. So that's JSON convert.serialized object data. That's all that we need to do. You can basically follow the same format regardless of what kind of data you're going to write, even if you're not using JSON. If you're using any other file-based way of storing data, you can follow basically the same pattern where you have a key and an IV using the AES provider, crypto transform, and crypto stream, and you're good to go. It doesn't have to be JSON data. If you want to generate new keys because you don't want to use the ones I'm using, which you definitely should not be using those, you can uncomment these two debug lines right here and do not override the key and the IV up here whenever we first create the provider. Instead, let it give you the auto-generated ones, and then you can just copy paste these two values above over the ones that I've provided. So now that we can encrypt data, let's see how do we decrypt it on load. Again, on the load data, we're going to do almost the exact same thing we did before, just slightly different. We'll define that read encrypted data function as a private T, read encrypted data, again of type T, that accepts a string path. In that try block, I'm going to define just T data and not assign it a value by default. Check if it's encrypted. We'll leave that block alone for a second, go to the else, and assign the data to be the line that we had before with the JSON convert deserialize object. So that way when it's not encrypted, it does exactly what it did before. If it is encrypted, we're going to do data equals read encrypted data that accepts a type T, passing in the path. These streams deal with bytes. They don't like to deal with strings. So what we're going to do is byte array file bytes equals file.readAllBytes, passing in the path. That gives us all the data that's already encrypted in this file into this byte array. And then we're going to do basically the same thing we did above, just in reverse to decrypt it. So we're going to do using AES provider equals AES.create. We're going to assign the AES provider key in IV the same way we did before, converting from the base64 string. We're going to create a new iCrypto transform using AES provider.create decryptor, pass it the key in the IV in the arguments here. In here, we're going to do something a little bit different. We're going to create a new memory stream using memory stream decryption stream equals new memory stream, passing in the file byte. So now we have a memory stream that has all of that file data already in it. And that's in place of having the file stream that we were using before. We're then going to do using crypto stream equals new crypto stream, again, passing in the decryption stream. This time, instead of the stream we're going to write to, we're going to pass in the stream that we want to read from first. Pass in that crypto transform that's going to understand how to translate that encrypted data to normal bytes. And for the third argument, we're going to do crypto stream mode.read because we want to read that data. We'll do using stream reader equals new stream reader that we pass into it, the crypto stream, because we want to read data out of that crypto stream. And finally, we can do string result equals reader.read to end. That's going to give us a string with all of our data that has been decrypted. So we can return JSON convert.deserialize object T, passing in that string that should be our deserializable JSON object. Because it might not be, because maybe our keys are wrong or somebody messed with the file. What we'll do is do a debug.log saying decrypted result if the following is not legible. Probably you have the wrong key or the IV, and then print out the result so that way we can see if it's wrong. Let's go back and see how does this work with encryption. So we'll open up the Unity editor. One quick note is the toggle button is tied to demo.toggle encryption, which just sets the encryption enabled to be true or false based on that check mark. If we go ahead and click play, the first thing I'll do is enable that encryption. We'll click serialize JSON and we'll see that it takes significantly longer. We were talking 40-50 milliseconds before. Now we're talking almost 200 milliseconds to save it and almost 500 milliseconds to load it. 460 milliseconds here versus the 200 that we had before. So adding encryption does make it take significantly longer. We're talking 4 times almost longer to write and about 2.5 times longer to read. But we pull up trusty Visual Studio, drag this player stats JSON there. It complains because this is not a really readable format and we get basically a bunch of gibberish in here. We have no idea what this says, and if I try to modify it, it's going to be really hard to do that. I had no idea what to modify here. And now to see what happens in case maybe we run into some problems. On the JSON data service, on the read encrypted data, what I'm going to do is comment out everything about passing in the key and the IV from our known values whenever we're reading the data. So you'll notice now, because we're not using the same key, we got an error. We have error reading save file. So if we go to the console, you'll see that's complaining here that, something's wrong with our decryption process. If I just change the IV of whatever we had before to a new thing, we'll see what happens if maybe the JSON serialization fails on the load. We've just changed the initialization vector here a little bit from whatever it was before. We'll see that there's an error reading save file. We mostly decrypted it, but at the beginning, something wasn't right, so it didn't come back with a proper JSON format, and we couldn't deserialize that. As I was saying towards the beginning of the video, it's not always best to use a text-based serialization because, well, first off, it's not the most optimized way to store data. Storing large quantities of data using something like a binary format makes it a lot more optimized. The primary use cases for using a JSON or text-based serialization, even if it's XML, is really the ease of use of this. It's very simple, you don't have to do a lot, and it just kind of works. However, using a binary formatting system is significantly more optimized. It's a lot faster to write data. It's significantly harder for a player to understand the data that they're modifying. They kind of have to guess and check at whatever they're modifying to see, hey, if I modify this, what changes in the game? Versus with a text-based serialization, probably have something like player health. It's going to be really easy for them to figure that out. Another potential option is you could store data in a database that may be using SQLite. That's an embedded, lightweight, really fast embedded database that's quite popular, very well supported as well. A couple of notes on the binary formatting is you should absolutely not use the binary formatter class. This has a really big security issue where if somebody specially crafts a file, they can take over the computer. So just don't use that. Use something like maybe Protobuf, which is a framework developed by Google that supports binary formatting. That'd be a great option. Remember as well, if you're going to store data on that player's local machine, you have to assume that they can modify that data. So a game that relies heavily on microtransactions by limiting the progression of the player may not be the best use case for having local storage because somebody could modify that and just negate all of your revenue options. If you're really hardcore about not wanting anybody to ever possibly cheat, storing this data on a remote server is really the best option. That's where the player is not going to be able to modify it. They can maybe modify it at runtime, but there's some ways you can kind of detect if somebody's doing that. I don't want to get too much into these other use cases, kind of going off too far already. In this video, what I hope that you got out was how to actually implement text-based serialization into your game to persist data across runs of your game, possibly encrypting that data to make it a little bit harder for the players to actually manipulate that data themselves, and discovered some potential alternatives in case text-based serialization doesn't work particularly well for your game. If you got value out of this video, please consider liking and subscribing to help the channel grow, reach more people, and add value to more people. This new video is posted every Tutorial Tuesday, and I'll see you next week.